Why come down? No, that's not what the guy yeah, only cover what you don't know his backstory. He's talking straight, but that doesn't don't let that fool you.
Can you turn on this light? Turn it on. No, off. No, no. अच्छा, fan will be off. Turn on the light. I need the fan. Good afternoon, everyone. Good afternoon. After a very, very, very long time. Yeah? Like, literally very long. How long? So I suppose you enjoyed the online sessions. No? Sitting in your bed, like having food and sir chalne do, sleeping. Acha. Online sessions, the only problem I have with online session is the response. Yeah, I would personally want everyone to be sitting on with their camera and like interacting every now and then, interrupting every now and then, like you do in class, like getting a point. But yeah, that's because the problem is if I don't get to like get your point, your ideas across, then I don't understand whether you understood or not. That's the problem. That's it. Acha. So redox, which that was the last chapter, right? Redox done. How was redox? Easy. Like in general, the questions that will appear in JEE Mains NEET will be very easy. The questions that might appear in JEE Advanced, Srivardhan. Acha. Huh? The stream is on. Only thing is the camera is on me. I want to show you doing all this nonsense exercise. Acha, chali, let's start. So today we are starting with chemical equilibrium. Now you remember this. How many of you have done this in class 10? Chemical equilibrium. Amazing, amazing. You have done a little part of ionic equilibrium as well, है ना? ठीक है, थोड़ा सा. Right. Now the main questions and the numerical part will come now, but you know the basics for sure. Okay. So give me. Okay, can some of you check if the stream is live and it is proper? It's fine? ठीक है. Let's start. So, chemical equilibrium. Who can help me out? Like most of you understand chemical equilibrium already. Can someone tell me what is a chemical equilibrium? Anyone? Chemical equilibrium? Niyantri? Huh? Just give me an idea. Rate of forward reaction equal to rate of backward reaction. Like directly to the point. Huh? No nonsense. What is rate of forward reaction? rate at which reactants are converting into products. Pranav, Shivardhan, क्या? नहीं तू उसको बोल रहा है वापस डाल. So it's done now. So close that matter. Thank you. Rate of forward, rate of back. Chemical equilibrium. The word itself has everything in it. It's an equilibrium. The things have come to a standstill on a macroscopic level. On a macroscopic level, like when you are looking at the solution, it won't change the color anymore. If some reaction happens in which color is bound to change, then after that point the color won't change anymore. It looks like it has come to a standstill. But is it at standstill? No. So can I say it is a dynamic equilibrium? How many of you didn't understand the word dynamic equilibrium? Now, say if a reaction is going in forward direction, it is bound to go in forward direction if you start with reactants. Reactants converting to products. Reactants converting to product. Slowly product concentration increase. Now after some time products realize, oh, even they can react. And again become the reactant. So as the product concentration increases, the reaction between the products increase and they start the backward journey. Forward, backward. You would have got to see this when weak acids were introduced to you. Have you heard of weak acids? Can you give me some example of weak acids? CH3COOH, right? We say that the degree of dissociation, is this word known to us? Degree of dissociation. Yeah. So let's say we have 1 mole CH3COOH molecule. When we say it's not a strong acid or when we say it's a weak acid, what we are trying to say is only some amount of CH3COOH will break down into CH3CO minus and H plus, right? Now when the reaction starts, for one molecule it will be like CH3OH, CH3COH broke down into CH3CO minus and H plus. For every molecule this will happen, CH3COH broke down into CH3CO minus H plus. After some time, the concentration of CH3CO minus and H plus increases. When it increases, then they realize, oh, we are weak acid. We are not stable. We are not going to give away our H plus. So CH3CO minus खड़ा है, H plus खड़ा है. They are like, bro, let's go back. Concentration of CH3CO minus and H plus increases. They start coming back. Now this forward backward process is continuously going on. But you will reach a point where when you are looking at it from a macroscopic level, you will see that if I have 10 molecules of CH3COOH, only 6 of them are in CH3CO minus and H plus. They don't have to be the same molecules. Like CH3CO minus H plus ban gaya, okay, we are 6 over here, now the reaction stops. No, this doesn't happen. They keep on going from this side to that side, this side to that side, but on a macroscopic level it looks like the reaction has stopped. So it's an equilibrium, yet the reaction is constantly happening, it is still continuously happening, backward, forward, but macroscopic level it has come to a standstill. That's why we call it dynamic equilibrium. Did you understand this? Now what is the whole aim of this chapter? The aim of this chapter is to understand what is an equilibrium. When we understand what is an equilibrium or any reaction, why does it go into an equilibrium? So I was telling you about equilibrium. Now what is the importance of equilibrium? Like the Haber's process, N2 plus H2 forms ammonia. Now this reaction, it can happen at very high temperature. But the problem is at a temperature which is around 500 degrees Celsius, when this reaction is happening, N2 and H2 are reacting forming ammonia. It is also going backward. So backward reaction is also forming. Now in industry, just imagine like if you are doing any kind of a reaction, let's say a precipitation reaction, you add silver nitrate and HCl, silver chloride precipitate. Let's say you wanted to create silver chloride. Reaction happened immediately, you got precipitate, reaction went to one end, you accomplished it. But most of the reactions in the nature are equilibriums. Now when they are in equilibrium and you want to make some commercial output out of it, you have to find out the behavior of that chemical equilibrium, and then you can mold it, you can take it forward in your own direction. So you would have heard of a person called Le Chatelier. So Le Chatelier is basically a person who was studying equilibrium and who was the first one who came up with this idea of doing N2 plus H2 gives ammonia. But he was not able to create an industrial process out of it. So in 1894, this guy, Le Chatelier, was struggling with the same problem. In 1903, 1904, Haber accomplished it. So that's why it became Haber's process. Otherwise, it would have been Le Chatelier's process. Otherwise, Haber wouldn't have got Nobel Prize. But anyways, no one wanted him to have the Nobel Prize. That's a different story. Coming back to this thing, N2 plus H2 gives ammonia. This reaction happens at a temperature around 450-500 degrees Celsius, pressure around 200 atmospheric pressure. Such a high temperature, he was able to establish the equilibrium such a way that it moved forward towards ammonia. Now, Le Chatelier's principle said that if there's an equilibrium, okay, equilibrium is what? It's a balance. If there's an equilibrium and if you start removing the product, the reaction is bound to go in forward direction. Why is it bound to go in forward direction? Because it again wants to reach the equilibrium. Getting my point? So that's the basic understanding of this chapter. This chapter will be talking about what is an equilibrium, what is an equilibrium constant, how we are going to deal with that and take this reaction in forward direction, and what factors affect the equilibrium constant. Okay? Now tell me one thing. When a reaction happens, you have something called equilibrium constant. You all remember this? Now equilibrium constant is giving us the concentration of products and concentration of reactants at equilibrium. How does it come into being? Like, can anyone help me understand how did we get to the point of equilibrium constant? This is something called law of mass action. Amazing. We all remember law of mass action. Can you tell me what is law of mass action? एक एक करके है ना, वो क्या लाइव जा रहे हैं ना, तो वो सब ऐसा है. So एक एक करके, yeah.
The chemical reaction is directly proportional to the concentration of the reactants.
Okay. Active mass or concentration? One and the
Molar concentrations.
Yeah, yeah. So the rate of the reaction, a rate of a forward reaction, is dependent upon the concentration of the reactant.
No, products for power.
Concentration of the.
So no, rate of any reaction is proportional to the concentration of the reactants only, right? For forward reaction it's the reactant, but for backward it's the product. So whatever is like reacting, that concentration is proportional to it.
Is it correct? Yeah.
Yeah, basically.
Did you understand what he said?
So is it reactants or products also?
Is it reactants or products? Let me put it in a very simple way. Is it reactant or product? Abhishek? Reactant. It's straightforward. देखो, let's put it like this. If a reaction is happening, N2 and H2 एक दूसरे को आके टकरा गए, तभी reaction होगा ना? N2 H2 डाल reaction. High pressure. You require a high pressure so that they come and collide with each other. When the collision takes place, reaction takes place. More the concentration of N2, more the concentration of hydrogen, more will be the probability of reaction. So what they came up with was a very simple idea that rate of reaction depends on the active mass. That was the word they used. Active mass is the mass or the amount of substance which is participating in the reaction. Got the idea? Now, rate can be in forward direction. Rate can be in backward direction. We just talk about equilibrium. So what is an equilibrium? When forward rate and backward rate becomes equal. That's how we started, right? That was the first thing you said. Rate of forward reaction equal to rate of backward reaction. So the active mass reacting the reactant side and the active mass reacting on the product side, they together define the equilibrium. They together define the rate of forward and backward reaction, and thereby we can determine the equilibrium constant. Now equilibrium constant can be in terms of concentration, it can be in terms of partial pressure, it can be in terms of say mole fraction. Okay, it can be depending on what you want, we can define it in that particular way. Is it clear? So this is a chapter that we will be starting with. Once we get an idea about chemical equilibrium, where reactants reacting forming product, products reacting forming reactant, then we will move on to the second part where I started with the weak acid thing, which will be equilibrium of ions. So that is second part of this chapter, which is called ionic equilibrium. Is it clear? Perfect. I suppose no one will doze off, because starting ka like 15-20 minutes is just terminology. So let's do it fast and then we will reach the questions part. So let's start. So what is an equilibrium? Well, equilibrium is a state in which opposing forces or influences, and it's a balanced state. So let's not do this part, like इसको बाद में मैं आराम से story बना के reel बना दूंगा, ठीक है? Let's go on this part. There can be mechanical equilibrium, there can be thermal equilibrium, and then there can be chemical equilibrium. Mechanical equilibrium we'll be talking about in physics, we'll be talking about all that stuff. Okay. In case of thermal equilibrium, its temperature we have discussed about the thermodynamics of a reaction. Okay. So it reaching a point, equal forward and backward point is a thermal equilibrium, but our main focus in this chapter is the chemical equilibrium. So to define chemical equilibrium, you can just put it in a very simple way: the rate of forward reaction is equal to rate of backward reaction. Just start with this statement: rate of forward reaction is equal to rate of backward reaction. Rate of forward reaction is equal to rate of backward reaction. We will talk about it from the perspective of concentration of reactants. We will talk about it from the perspective of graph defining concentration and partial pressure of the reactants and products. Done? So time pass. So what are the types of reaction? अरे बाहर क्यों आ गया? So there are multiple types of reactions: homogeneous, heterogeneous, exothermic, endothermic. So we will talk about each of these cases, okay, and how equilibrium can be affected or can be understood for each of these type of reactions. Okay. So first we talk about homogeneous reaction. So what is a homogeneous reaction? You want to tell me? All the reactants are in same state, right? It can be like all of them are in gas, all of them are in a solution form, all of them are in maybe solid form. We generally don't talk about solid reactants too much, like all of them in solid is a something we can't determine the concentration and all. But generally for gas and liquid state, like all the reactant and product in same state will be a homogeneous reaction. So let's put an example so that you will remember this. N2 plus H2 gives ammonia. It's an example of homogeneous reaction. Done? Then we talk about heterogeneous reaction, in which all the reactants and products are not in same phase. So this is an example of heterogeneous reaction. Done? Then we talk about exothermic reactions which release heat. And इनको मत लिखो अभी, इसको इसके बारे में we'll talk about it later. Like these like N2 plus H2 gives ammonia is an exothermic reaction, but obviously we do it at such a high temperature that we don't realize it's an exothermic process. It is carried out at 500 degrees Celsius and a very high temperature. And then endothermic reactions are the reactions in which heat is absorbed. So you can write down this example for endothermic reaction. N2 plus O2 plus heat gives NO. Are you able to see this properly? Okay. N2 plus O2 forming NO. Can you think about it? Nitrogen reacting with oxygen. We have like, right, 71% nitrogen, 78% nitrogen, 21% oxygen. आपस में react कर रहे हैं. Is it possible? Is it possible? अब बोल रहे हैं यार, it's happening. It is possible at a very high temperature. At temperature about 1200 degrees Celsius and around up to 3000 degrees Celsius, this reaction is spontaneous. You remember what is spontaneous? What is spontaneous? What does it mean when we say reaction is spontaneous? It happens by itself. Delta G. Delta G is negative. That's the point I want to hear from you guys. Okay? When I say spontaneous reaction, don't please assume it's happened by itself. Just say delta G is negative for this reaction. Okay? So N2 plus O2 forms NO, is spontaneous above 1200 degrees Celsius up to 3000 degrees Celsius. If you want to carry it out at room temperature, you can use electric arc. A silent electric discharge can also carry out this reaction, which is convert N2 and O2 into a compound which is NO, nitrogen oxide. This compound is not stable. If it comes in contact with oxygen, it reacts. At room temperature, NO reacts with oxygen to form NO2, brown colored gas. Have you heard of it? So we'll talk about this reaction in detail, okay, later, but not now in this chapter. So if we talk about endothermic and exothermic reactions and their comparison, right? In case of exothermic, heat is evolved. We know all these points. Obviously the product are more stable, that's why heat is releasing. Do you remember, have I ever discussed energetics with you? Energetics of a reaction? नहीं? अच्छा ठीक है. Imagine this is the energy diagram versus time, E versus T. Abhay, don't talk please. Thank you. Now, energetics is basically it's the defining process for every chemical reaction. Like we know some chemical reaction absorb heat, some will give heat, some will have reactants at a higher energy, some will have products at a higher energy. So this is, let's suppose, reactant. Can you tell me one thing? If I have a reactant at higher energy and if I have a reactant at lower energy, which is more stable? Lower energy. We have done this for electrons as well. Electrons jumping from higher energy to lower energy. So if energy is more, stability is less. Is it clear? Huh? Sure then? No, okay. Now imagine you have a reactant which is at higher energy and it is going to convert into a product which is at lower energy. Now path of the reaction, okay, this is the path of the reaction, we call it mechanism. We will discuss about this path in detail in chemical kinetics, which comes in class 12th, okay. Like we will talk about the kinetics of a reaction, mechanism of a reaction at that time. So that is when I will be able to explain you why there is a jump. But let me give you a very simple example to start with. We all like fire. Yeah, why not, right? Now you remember, like ऐसा नहीं होता ना घर पे ऐसा सिलेंडर से ऐसा गैस ऑन किया लाग लग गया, ऐसा नहीं होता ना, right? When you just open it, after opening the knob you require a lighter, you have to give that initial spark. Imagine for the very first molecule of butane and oxygen. Yes, that's what the peak is. I have to take these reactants to a point जिसके बाद उसको धकेल दो, उसके बाद it happens by itself. In physics, what do we say? This is the point, right? This is the point where you have a unstable equilibrium. This is the point of unstable equilibrium. Why? It can fall on each of the side, either of the side. थोड़ा सा धक्का दे दो इधर चला जाएगा, इधर धक्का दे दो इधर चला जाएगा. ठीक है? Just imagine you took this molecules to this point. This energy is called EA, which is called activation energy. The ignition temperature or ignition energy or the activation energy, one and the same thing. We provide that spark. But once you provide that spark, once first molecules go to this part, uske baad this thing happens by itself. Then it will go. Now let's imagine this. In this process, if I ask about the energy that has to be provided, so let's call this X. And the energy that got released, let's say this is minus Y, because I am putting it in thermodynamics way. Energy, heat evolved, negative, heat provided, positive. So can you see for this overall reaction, the total energy involved is X minus Y? Yeah? If the value of X minus Y is negative, the reaction is exothermic. If the value of X minus Y is positive, reaction is endothermic. So if a reactant is unstable, product is stable, which means overall change in the reaction. Can you see the change in the reaction? This is the value of X minus Y. Getting my point?
Yes, sir.
So this is energetics of a chemical reaction. So when we say exothermic, endothermic, we are actually talking about this whole process. If the reactant is stable, let's say reactant is stable and product is unstable. So can you imagine the second graph where the reactant is stable? So if reactant is stable and the product is unstable, can you imagine now? This is an endothermic reaction. So I hope these basics are clear. I will come back to this point again when I will be starting GOC in organic chemistry. In organic chemistry, we will be talking about the mechanism of a reaction through energetics diagram. We will talk about the process through energetic diagram. So this hump which is there, which is called E activation, there can be multiple humps. So there can be reactions with this. What does it mean? It goes through two different processes. Got the idea? That's it. That's more than enough. Let's move ahead. So coming back to endothermic and exothermic reactions, I suppose I have made the second point clear. Products are stable. In this case, products are less stable. This is slow, that is fast. Now exothermic, it is like the energy is releasing. So one molecule reacts, produces energy. The energy that first molecule produced will be used, some amount of that will be used by second molecule to produce next reaction, which will again produce energy, which will be like some amount of that energy will be taken by third molecule, and so on. In case of endothermic reaction, you are already providing the heat. The reaction will not proceed until and unless you have provided that much heat, because it has to go to that part. So you have to give that much heat. Once you provide that much heat, all the molecules which are there will react immediately. Got the idea? Like, let me give you an example. Calcium carbonate. You know calcium carbonate marble. Decomposition of calcium carbonate. We have studied this from class 10th. Do you know at what temperature it takes place? Around 1200 degrees Celsius. 1000 to 1200 degrees Celsius, calcium carbonate decomposes into calcium oxide plus carbon dioxide. But at 800 degrees Celsius, nothing will happen, because energy is not enough. It is going till this part, coming back. 900, going there, coming back. 1000 just reached there, coming back. 1400 कर दो. Dhadal, dhadal, dhadal. Everyone will react. That's why fast. Getting my point? Are you with me? Chalo, favorable at low temperature, favorable at high temperature. I will discuss about this thing again when we will talk about Le-Chatelier's principle. Okay? Because this reaction requires energy. High temperature is favorable. Since this reaction is giving off energy, low temperature is favorable. So just copy down this one, then we'll move on. Comparison between endothermic, exothermic. Done? I just found this funny thing online, so I was like, hey, let's get this. Yeah? Yeah? So it's got 200 something. Same the cable price, only with the light. Huh? I will tell you the reason I bought it. Like what happens in my car, the cable generally becomes loose, and I stopped. I don't realize that it has stopped charging. So when it is lit, I am like, chalo chalo, music lagao, chalne do. Okay, done. Now please have a look at these reactions. Can you tell something common in all these reactions? What is common in all these reactions? Don't write it down. We all know all of these reactions. Like they are exothermic. Okay, neutralization is precipitation. Combustion, yes. Redox, can't say. Okay. Everything other than combustion is a displacement. No, this is double displacement. This is double displacement. This is displacement. This is displacement. What is common? They are all irreversible reaction. They are all one side. They all will reach to the end product. Strong acid, strong base. Together, there is no coming back in this reaction. Similarly, this also reached the end point. So they are all technically irreversible reactions. The reaction takes place in only forward direction, therefore irreversible. ठीक है. I don't know what to write all this stuff. Like you already know this, right? Yes, sir. So just do you want to mention? Yeah, skip. So let's move on to reversible. So these are some examples of reversible reaction. We have already written this down. Now whenever we have a reversible reaction, we denote it using this symbol, which is forward, backward, simultaneously. Moving forward, we will also play around with this symbol. Let's say this forward is small and backward is big. So backward ज़्यादा हो रहा है, forward थोड़ा हो रहा है. Backward चलता जाएगा. It will reach a point where it will become equal. Just to denote it, we will talk about it from a numerical perspective, but we will talk about something called reaction quotient and K equilibrium, and we will compare that, right? KCQC, right? And the idea is simply this thing: which arrow is bigger, which arrow is smaller, and it will continue till rate of forward becomes equal to rate of backward. ठीक है? अभय तो बेचारा बीच में फंस गया, है ना? Vittal, I will throw you out.
Thank you, sir.
Okay. So, yeah, these are some points that can fetch you couple of marks in your board examination. So reversible versus irreversible. Let's just have a look at the point. Like they are all very straightforward, right? Any point which is not understand. We will talk about law of mass action in just next 5 minutes. But rest of the things are pretty straightforward.
So what was
No, second one. Third one. The products are less stable. The products are less stable, that's why they are reactive. They are reactive, that's why backward reaction is happening.
So then for exothermic reaction, it will give out heat energy or something.
So for an exothermic reaction, the reaction is irreversible if the difference between reactant and product is too much. If they are very close, very slightly exothermic, so this can go here and this can again come back here. So the difference in their energies might not be too high, or we take the we change the conditions to that level that the difference does not remain that high. Just think about it. N2 plus H2 gives ammonia. This reaction won't be a reaction at room temperature. N2 and H2 mix it at room temperature, nothing will happen. But we take it to a point in by increasing the temperature and all, so that the forward and backward reaction, the K equilibrium value, the E activation becomes low. So it happens very fast, forward and backward. So that's what it is. The product is not stable, that's why it is coming back to the reactant. If we talk about it from the perspective of a weak acid, the acid is weak, that's why it is again taking back the H plus and forming the acid, the CH3COH molecule. Okay, but we will use this terminology or this example in ionic equilibrium. But I hope I have made that clarity. Okay, done. Have you copied it down? Second point, complete conversion of reactant into product is not possible because this is a reversible reaction. जैसा product बनेगा, product वापस reactant बना देगा. By the time reactant product में convert होगा, product reactant में convert हो जाएगा. So वो passing the parcel चलता रहेगा. Done? Just write it down. Please write them down. Product is less stable, that's why it is reacting again. Product अगर stable होता तो it wouldn't have reacted. So just imagine a weak acid and a strong base. When they react, the salt of weak acid and a strong base is a basic salt. You remember we call it basic salt. Why? Because that salt will take H plus from the water molecule and form the reactant. So since product was not stable, it again got converted back to the reactant. Make sense? Yeah, just write it. It's not too big, right? Sorry for disturbing you guys. I'm really sorry for that. I didn't mean to. I was just scrolling around. Okay? Then it's alright. If possible, just check the live as well and give me a like. Done, na? Thank you. Done. Can we move forward? Abhishek, you were there on Redox cast session? ठीक है. So how much time? Cast?
We didn't have sir. It was starting from
Redox cast.
yeah.
The one that I took.
Yes sir, that was it.
Yeah. This time Saurav sir will be taking gaseous state. Yes. So that's there only in advance. What? It's very easy. It won't like. The second part is real gas, which is a bit difficult, but 2 sessions will be required to cover it. When do you have maths ka gas? Yesterday you had maths and physics. Arey. What do you have on Saturday? Huh? Physics. School physics. Serious, yeah. Now I want to set the cash session because Saurav sir was delayed on that day. So I want to keep session on one of the days. When should I keep that? You have Diwali holidays from?
Thursday, Friday, Saturday, Sunday.
Oh, Thursday, Friday, Saturday, Sunday.
Monday also. Monday is not. So basically we got scammed with Mondays. On Thursday, Friday. Also, Saturday, so yeah, we got scammed. We got
Same time holiday for both school and Sunday.
Same time, right?
I think same 4 days.
अच्छा अच्छा. Diwali is on Thursday, क्या? 31st. Thursday. अरे यार. Can you repeat?
Second also Diwali holidays from 31st to 35th.
Yes, yes.
I don't think we can have class that.
No, we can't. Yeah. No, so I was planning to. I'm not giving
you know
it.
there's this AI thing that you can like upload a whole YouTube video and like make it into very short.
I want to do that. Yes. Can you suggest me what is the name of it? Okay, we'll touch. Let me do that. Let me try that. It can make reels out of it, right? Small reels and.
Yes sir, yes sir. Like 1 minute videos out of like a big
Yeah. Everyone is done with it? Okay. I don't want you to write all this stuff. Okay. Let's just talk about it. Physical equilibrium is basically rain and evaporation stuff, right? Water evaporates, goes into cloud rains, come back into water. So this is a physical equilibrium on a closed system. Okay, this is very important. Please remember that an equilibrium can be set up only in a closed system. I think you have already studied this in your class 10, but understand this, like in a closed system, the mass will not get out of the system. The energy will not get out of the system. So it will keep on converting from one form to another. So for equilibrium, this is like the foremost and the most important thing. It has to be a closed system. Okay? So physical equilibrium is basically a liquid water going into this gas, and if it escapes, arey wow, very nice animation. Vapor coming back. Now you just close it. Vapor coming back to this liquid form. So I just got it from somewhere. Okay, so very nice. Huh? So vapors are formed, vapors again go back into the liquid form. Let me talk about this part. Just give me 1 minute. I will have to edit it. Yeah. It's alright, it's alright. Come back to this part. So there's a chapter in class 12 which is by the name solutions. In solutions chapter, we talk about a term called vapor pressure. Um, if you have realized this part, like whatever water is there on the surface of the earth, it will convert to some vapor form. Now imagine that inside a closed system. In a closed system, the particles of liquid water are constantly evaporating. Now the evaporation process does not have to go to the boiling point. Like you don't have to take water to 100 degrees Celsius to cause this process. It is a surface phenomena and it will keep on happening. So if you have felt this, like if you have ever had hot tea in a cup, it's like it cools down slowly as compared to hot tea on a saucer, right? So the same thing, it's basically the number of particles evaporating from the surface, but eventually this will reach a point which is called equilibrium, where the number of particles going to the this gaseous form and then coming back to the liquid form reaches an equilibrium. Now this equilibrium is dependent on multiple things. Give me one simple answer. When you go to mountain area, the boiling process, the boiling point, is it like for water, is it more than 100 or less than 100? Why less than 100? Huh? Atmospheric pressure is less. So what happens? It is easy for the molecules to escape, or I would say no one is forcing the molecule to come back into the liquid form. No one is forcing the molecule to come out, stopping the molecule from coming out. Okay, same thing. Now when you go at a higher pressure, the boiling point will increase. Do you know we use pressure cooker? So the whole idea of pressure cooker is increase the boiling point. So the water which would have boiled off at 100 degrees Celsius in a pressure cooker might boil off at 105, 110 degrees Celsius. So the idea is, if the temperature of water goes to 105, 110, the process of cooking of the rice or whatever we are cooking, it happens fast. Got the idea? Now that is because of external pressure. Second thing, what if I add some salt to this liquid? What will happen to the boiling point if this liquid has salt? Will it be more or less? How many of you think more? How many of you think it will be less? How can we explain this? Let's start with less. Less? Nahin. Why do you think it should go less? Why should boiling point become less? Any reason? Molecules are moving faster. Collisions will be higher. Okay. Who all raced for the boiling point will go higher? Can you explain why the boiling point will go higher? More impurity? I will, you are on the right track. I will just help you with the explanation part. If you have more impurities in the liquid, please focus here. If you have salt, sugar or any kind of impurity in the liquid, the surface will become less. Like on the surface, let's say 500 molecules would have stayed on the surface, but out of those 500, 50 are sodium chloride. So they won't, like, they will cover that surface area. So we just talked about it when I said if you have tea in a cup and a tea in a saucer, the one in the saucer will cool down fast because more surface area is available. For a impure solution or for a solution with some salt or some kind of an impurity, the surface area will become less. So we will go about details of this physical equilibrium in chapter solutions in class 12. So in chemical equilibrium, there are some part that we will study in chapter chemical kinetics, some part we will study in the chapter solutions. There is one more part to chemical equilibrium, which is a catalyst. Do you know what catalyst does to a reaction? It speeds up the reaction. It can even slow down the reaction. You can control the rate of reaction. ठीक है? Kinetics, speed, movement can be controlled. You can increase, you can decrease. So we will talk about catalyst in the chapter surface chemistry. Again, class 12. Did you get that? Chalo, let's move on to the chemical equilibrium part. So our today's main focus is on chemical equilibrium. I'll just skip this part. You already know all of this stuff. Very nice, this GIF and all that stuff. Nice PPT. Yeah, very nice. Absolutely amazing. Okay. So now this is the part I want you to copy. We'll talk about chemical equilibrium. Okay. Before any graph appears, in the beginning we just said something. Rate of reaction depends upon the active mass. What is active mass? Number of amount of reactant colliding and reacting. Okay. What will happen to the rate of reaction with time? Because we have rate of reaction, two rate of reaction, forward and backward. Let's talk about forward reaction. What will happen to the forward reaction? Forward reaction decreases. Why would it decrease? Because amount of reactant decreases. Please don't talk among yourself. Thank you so much. Thank you. Rate of forward reaction decreases because the amount of reactant decreases. So if I have a rate of reaction for forward, it might start somewhere here from some finite high value and it will slowly decrease. And what about rate of backward reaction? It will start from zero because initially there is no product, so there is no backward reaction. So it will start from this point. It will increase. Now imagine if the reaction was irreversible reaction. If the reaction was irreversible, so there is no backward reaction happening. So your forward reaction would just come down. It might come down in a straight line, it might come down like a curve, we don't know. That depends on the, again, chapter chemical kinetics, class 12. But if we have a reversible reaction, the rate of forward reaction will decrease and come to a constant point. Rate of backward reaction will increase and come to a constant. Okay. Now, before I move ahead, I just want to draw on this very surface. Okay, because where's the pen? Yeah. So if this is my forward reaction and this is my backward reaction, is it an equilibrium? Can it reach an equilibrium? Okay, let me put it as A. Okay, A, B, C. Please, guys, please, thoda, don't discuss. Can you tell me A, B, C? Which one is a equilibrium? How many of you think? See, let me just tell you what is C. Rate of forward and rate of backward are How many of you think C? C? C. How many of you think B? B? Or A? A? So we started this chapter with Nihan saying rate of forward this was the guy who defined it. Rate of forward, rate of backward equal करना है. The reason I ask you this is a question from me. This is the rate ka graph. Rate has to be equal. Rate of forward has to become equal to rate of backward. What you are able to remember is the concentration of the graph. Are you getting my point? Chalo, theek hai. That's why I didn't go ahead with this. Chalo, perfect. So, initial concentration. So now we are talking about the rate of reaction. N2 plus H2 gives NH3. Beautiful, such a beautiful. Ah, amazing, amazing. Going forward the heat. Oh my God. Such a beautiful PPT यार. पता नहीं यार, इतना अच्छा काम मैं करता कैसे हूँ? Oh, too long. Bribing and all, it takes a lot of time. So, please draw this graph. And also है ना इस पार्ट को underline करना. ये जो है ना rate of reaction, underline this part, highlight it, whatever way. Understand, this is rate of reaction, not concentration. ठीक है ना? Yes sir. Perfect. A, B, C, all the three are correct then. If it was concentration, so rate of forward, rate of backward, when it becomes equal, the concentration becomes constant. The concentration is not changing. So in all the three graphs, the concentration reached a constant. So all the three were for equilibrium, given it was concentration versus time. But rate of reaction and forward and backward, it has to be. Yeah. No, even dynamic equilibrium, the rate of forward and backward has to be equal. In second graph, rate of forward was greater than rate of backward. So it has still not reached an equilibrium. ठीक है? Only the third graph was equilibrium. We'll talk about concentration, then it will get clear to you. Don't worry. Are we done? Amazing. Can you इसको थोड़ा सा साइड में कर लेना श्रीवर्धन? I don't want to hit it again and again. Thank you. Okay. Now there are some cases even for forward and backward reaction. Okay. Now in this case you can see that rate of forward, rate of backward have become equal, but the extent by which rate of forward reaction decreases, it's higher. Rate of backward reaction, it does not have to go too high. What does it mean is basically going to talk about the concentration. So in this case, forward reaction is more dominant than the backward reaction. So can I say the product concentration will be higher than reactant concentration, although they have reached a state of equilibrium. But since this is higher, this dip is higher, which means the product side is a little more than reactant side. So again, one more point to be highlighted. Equilibrium does not mean that the concentration of reactant and concentration of product will be equal. This graph suggests that point. Equilibrium does not mean that the concentration of reactants become equal to concentration of products. The rate has to become equal. Perfect? So this is case 1. Just write down case 1, forward reaction more dominant. Product greater than reactant. Forward reaction ज़्यादा हो गया ना? So the extent till which forward reaction went was higher, but the extent till which backward reaction went was not that high. So product is greater than. ठीक है? Should just write this, Anirudh. Forward reaction is dominant, which means the product side is higher. It has like that. ठीक है? Then case 2. Case 2 is this. In this case, you can say the reverse reaction is dominant. Forward reaction happened, but reverse was much more dominant.
Well, sir, the forward reaction is exothermic, backward is the endothermic.
Technically, you can say that because imagine heat as a reactant or a product. So in endothermic reaction, heat is reactant. In exothermic, it is product. Make sense? Can we move ahead? Can we move ahead? So please write down these 6 points. If you remember, we have already discussed this part. Please focus. First point, reactants and products. In case of an equilibrium, both are present. Then second is at equilibrium, neither forward reaction nor reverse reaction has ceased. So it's a dynamic equilibrium. So both reactions can continue to proceed in opposite direction with equal rates, because we said rate of forward equal to rate of backward. So dynamic equilibrium. Then the third is concentration of reactant and products reach a constant value, and these are equilibrium concentrations. So the reactants and product reach a constant value, but they don't have to be equal. They can be equal, but they cannot be equal as well. Point number 4 is a catalyst does not affect the position of equilibrium. So catalyst can affect the rate. It can affect the rate of moving forward, coming backward, but it won't increase the product, it won't decrease the reactant, nothing like that will happen. Fifth is change in concentration, pressure, volume and temperature can change the equilibrium position, because temperature, pressure, volume, all of these changes the active mass. Concentration might change. If you increase the pressure, if you keep the temperature constant, then volume will decrease. Volume will decrease, concentration will change. If you increase the temperature, keep pressure constant, temperature increase, volume increases, so concentration changes. Are you getting my point? So active mass is basically the concentration. If it changes, equilibrium position changes. And the last point, as we discussed, equilibrium can only exist in a closed system. Yes.
Suppose there's a catalyst only for the forward reaction. Won't there be more product
So
in that?
I will put it like this, Amrita. Catalyst is just going to decrease the activation energy. You know the hump that I showed? It will just decrease the activation energy. So what it will do, it will affect the rate of reaction, but it cannot affect just single reaction. क्योंकि rate of forward reaction increase करेगा, so concentration of product बढ़ जाएगा, which will increase the rate of backward reaction, है ना? So what catalyst will do, let's say some reaction is taking 10 hours to carry out, catalyst might just reduce the time to 3 hours, ठीक है? But it will not shift the equilibrium position. हाँ.
Why do we choose to define it as like a concentration change in concentration, like with respect to time? Like why is it the initial concept? Why is it like a change? Is it just an invented parameter for like for simplicity and calculation? That's why we say rate is just concentration. We say that R is equal to concentration of the reactants. Right? The
Yes.
initial, it's the initial procedure. Then we introduce constant, and then the constant
Then?
then we introduce the constant, we said the constant will sort of gauge how fast it's going.
Yeah,
And then
yeah.
we said that this parameter is telling us how fast it's going. But why do we do like change in concentration with respect to like this is the initial
Change in concentration.
the initial concentration, right?
Yeah.
Reactants.
Okay. So I got your question. I got your question. So, ठीक है. Let me just highlight what question Aditi is asking. She's saying, when we are talking about the rate, why are we not talking about the change in concentration per unit time? Am I correct? Why are we talking about concentration at any given time and determining rate on the basis of that? Change in concentration per unit time will give me the speed of reaction. Change in concentration per unit time will be like, अच्छा 1 mole से half mole होने में कितना time लगेगा? That is kinetics of a reaction. When I am talking about equilibrium, at equilibrium the concentration has reached a constant point. The concentration is now not changing. Are you getting my point? At equilibrium, the amount of product and the amount of reactant is constant. So, at equilibrium, if I put the explanation of the rate of change of concentration will be rate of reaction, but equilibrium पे तो concentration change ही नहीं हो रहा. How am I saying?
When you study the reaction, there is a change, right? We think the change not happening is when we calculate. This is after this is going to equilibrium.
Let's put it like this, Aditi. The speed of a reaction, if we talk about that, it will change with time. Initial concentration was very high, speed was very high. The graph that we drew, right? So the rate is constantly changing. Our focus is on the point where it reaches an equilibrium. Okay? If we want to talk about rate of change of reaction, okay, or the speed of the reaction, that we will discuss in next year chemical kinetics chapter. So that is kinetics of a reaction. किस स्पीड पे रिएक्शन हो रहा है, हाउ मच टाइम विल इट टेक फॉर अ रिएक्शन टू हैपन. बट जनरली काइनेटिक्स इज डिस्कस फॉर अ रिएक्शन विच इज irreversible, because we want the concentration to change, we want to see the rate of change of concentration per unit time. Getting my point? But right now we are at a position where we are talking about a reaction which is going in both the direction, and we think it has stopped, but it has not stopped. I will give you a very good example of this. If possible, I can make a video on this in a couple of weeks. Have you heard of this? Have you seen this iodine clock reaction? Iodine clock reaction. Okay, let it be. You would have seen one reaction in which you have a clear solvent, okay, and suddenly it's there, it changes its color, it becomes black. ठीक है? फिर you just keep it like this, and after some time it will again come back to colorless. So it will just keep on jumping from colorless to black, black to colorless, colorless to black, black to colorless. It is called iodine clock reaction. We can change the rate of that reaction. So it's basically forward, backward, both the reactions are happening. It will stop when it will reach an equilibrium. So the point is, those kind of reactions in which both the direction movement is happening, we have to reach a point of equilibrium. So I will also, once we start solving the numerical, I will be using terms like at t equal to 0, concentration of reactant falana falana. At t equal to infinity, concentration of the reactant and product will be something XYZ. So we are not talking about what happens in between t0 to t infinity, because that will become part of chemical kinetics then. ठीक है? चलो, let's start with the next one, law of mass action. 1864. That is when it was obtained by these two interesting people. Oh, we don't have their photo. Sorry? Guldberg and Vaj. They were like Jija Sala. Okay, that was the relationship between them. And they came up with this very interesting this law which is called law of mass action. It's absolutely theoretical. Let me be very clear about this. This law is a theoretical law which assumes that the rate of a reaction is dependent only on the concentration of the reactants. Please. So concentration, we generally denote it in the terms of square bracket. Concentration, which is called active mass, it is basically moles of certain solute or certain reactant per unit volume of the solution. So the rate of this reaction will be dependent on, at any given point, it will be dependent on concentration of the reactant to its stoichiometric coefficient in a balanced chemical reaction. Very nice. Call this rate constant, or you can also call it specific rate constant. What is specific rate constant? Imagine the concentrations were 1 1 unity, then the rate of reaction will directly be equal to K. So that's why we call it specific rate constant as well. So just write down done.
So one second.
Yeah.
If then rate is rate and then concentration, so then what is like, is K anything related like speed or
Sorry.
what is K denote in terms of distance?
Rate. What does rate denote? Oh, K denote. K denotes basically when the concentration is unity. When the concentration is, both of the concentrations are 1 molar, then the rate of that reaction will be K. The speed of that reaction will be K. So speed when concentration is 1, when both these values are 1. So that's why I use the term specific rate constant. It's just a constant which is defining the forward reaction or one side reaction. Okay? We are assuming as if this reaction is going to the end, product ban gaya. So what will happen? You just imagine it like this. Initially the rate of reaction is high. You remember we drew the graph like this. The rate of the reaction was very high, and slowly rate of reaction decreased because the amount of both the substance, the active mass of both the substances decreased. Done? So let's write down the statement. The rate of a chemical reaction is directly proportional to the product of active masses of the reactants, with each active mass term raised to the power equal to stoichiometric coefficient in the balanced chemical reaction. So that is law of mass action.
Sir, I have a doubt.
Yeah?
Is there any unit for the rate of
Yeah. Yeah. So it will be, so rate is change in concentration to the power. There will be a power because there is a stoichiometric coefficient. So it will be to the power of that coefficient. Huh? Hey, this is just about any reaction from going one side to another. And for reversible, we will apply it for both the sides, and then we will get rate of forward, rate of backward, K forward, K backward, and then we'll.
Table is in the table for irreversible law mass action.
Irreversible law of mass action is not applicable because at infinity the concentration is over, the reaction stops. So we don't use it because in case of an irreversible reaction, this powers are not stoichiometric coefficient. They are something else. So that again we will discuss in chemical kinetics. Yes.
So we are talking about T0 to infinity. What will be?
Yeah. Yes. Done? अरे यार Yeah, let's copy this part. ठीक है? So there is a certain reaction. So for this reaction, for this given reaction, rate of forward reaction is this, rate of backward reaction is this, and at equilibrium rate of forward becomes equal to rate of backward. So what will happen? At equilibrium we can say this equals to this. What is the rate of forward reaction? Specific constant, rate constant into a to the power a, b to the power b, rate constant. This is reverse reaction. Backward you can write it back as well. C to the power c, d to the power d. So if we rearrange it, we get kf, k forward by k backward as product concentration to the power of their stoichiometric coefficient upon reactant concentration to their stoichiometric coefficient, and this is termed as equilibrium constant. K forward upon K backward. ठीक है? अब भाई क्लियर है? You got it? ठीक. Can I have your module, please? श्रीवर्धन अपना पार्टी रह गया ना, वॉरियर पार्टी.
And it's not even time to can't write exam. But if it doesn't, go back and try atom bomb. That's what oh my god, sir, look at your bottle.
Is it?
Your bottle.
Yeah.
It looks like a huge thing for cough syrup.
It looks like a
Huge bottle for cough syrup because oh, they don't sell cough syrup in this bulk.
So you know what is huge? Are we done with this? Please write down. So equilibrium constant is defined as product of the equilibrium concentration of products to of reactants with concentration of each substance equal to its stoichiometric coefficient in balanced reaction. Okay, we have written it down. This is just a statement form. Now we have introduced something called C. What is C? When we are talking about equilibrium constant for a reaction, when we are expressing all the concentrations in moles per liter in the form of concentration. Now imagine if instead of using concentrations, you are using partial pressure. So partial pressure also behaves in the same way. So partial pressure, if you are using partial pressure, instead of Kc, it will become Kp. Instead of Kc, it becomes Kp. In Kp, you will have partial pressure to the power of its stoichiometric coefficient, right? Instead of concentration, you will have partial pressures to the power of stoichiometric coefficient. Oh, we haven't studied partial pressure? Okay. ठीक है, no worries. We'll have to take one example for that. So there goes my slip test. छोड़ो. Are we done writing this?
So one second.
Do you remember mole fraction? Mole fraction was number of moles of particular substance upon total number of moles. Partial pressure is when you have all the, like all whatever we are defining, they are all in gaseous form. Then pressure of a certain substance upon the total pressure is partial pressure. So mole fraction is moles of certain substance upon total number of moles. Partial pressure is pressure of certain substance upon total number of total pressure of the this whatever it is. नहीं, so open system में तो अपन equilibrium कर ही नहीं रहे. It has to be done in closed system. Okay. Imagine Earth is a closed system. Okay. Now 71% is nitrogen. 78% is nitrogen. 22% oxygen मान लेते हैं. ठीक है? For the sake of discussion. Can you tell me the partial pressure of nitrogen? Okay, let me define the question. Earth is a closed system. About its atmosphere, we are saying that the total amount of nitrogen is 78%. Total amount of oxygen 22%. Can we define the partial pressure of nitrogen and partial pressure of oxygen? So partial pressure of N2 and partial pressure of O2. Let us understand first thing. How many of you know ideal gas equation? All of you know this? Pretty simple. Pressure of any given gas is dependent on its moles. P pressure, V volume, N number of moles, R constant, gas constant, T temperature. So pressure of a substance is dependent on number of moles. Imagine I am keeping volume constant, I am keeping temperature constant. If pressure increases, number of particle increases. You want to try this? Just take your hand, close it. Once you close it, try to blow air inside it. Try it. Close it. Air should not come out of this thing. It should not come out of any part. If it is coming out, then the system is not a closed system. It has to be a closed system. So inside a closed system, if you increase the number of what I am trying to say is number of moles increase, pressure increase, we can feel it inside our mouth, we can feel it inside this. Got the idea? What we are doing, we are keeping volume constant. Imagine if you keep pressure constant, volume is allowed to change. Pressure constant, atmospheric pressure constant, blow inside a balloon. When you blow inside a balloon, you are increasing the number of moles of gas inside the balloon. External pressure constant, volume increasing. So N increases, volume increases. Are you getting this point? Okay. So this is simple gas law. PV is equal to nRT. If you increase the temperature and keep number of moles constant, or maybe pressure also constant, then volume increase. If you keep volume constant, pressure increase. So they are dependent on each other like this. Now having said that, we understood one very simple point over here, that pressure is dependent on number of moles. More the number of moles, more the gas, more is the pressure. So in this case, when I am supposed to find out partial pressure, it cannot be on the mass percentage. This is mass percentage, na? Got it? So first assume that the gas I have is 100 grams. If I have 100 grams of gas, 78 grams is nitrogen, 22 grams is oxygen. So the partial pressure of nitrogen, what is partial pressure of nitrogen? Moles of nitrogen 70 by 28 upon moles of total number of moles. Now what are the total number of moles? Total number of moles is moles of nitrogen plus moles of oxygen. This is, do you know this term? This is mole fraction, na? This multiplied by total pressure. Did you get this point? If a gas is applying certain pressure, then partial pressure is directly proportional to mole fraction. Got it? Okay. So can I also say that mole fraction of nitrogen is nothing but partial pressure of nitrogen upon total pressure? Yeah? Are you able to understand this correlationship? Instead of moles, we are taking pressure. You did this for volume if you remember. In mole concept, 200 ml of hydrogen reacts with 100 ml of oxygen at NTP, STP, keeping standard temperature pressure. So instead of moles, we directly use volume. Now in this case, instead of mole, can I directly use pressure? Got the idea? All of you got the idea of partial pressure? Now just introduce this partial pressure in the concentration part. So if Kc is concentration of C to the power C, concentration of D to the power D upon concentration of A to the power A and concentration of B to the power B. For Kp, what is Kp? When you are doing this for gas, you just do it for partial pressure of C to the power C, partial pressure of D to the power D upon partial pressure of A to the power A into partial pressure of B to the power B. Did you get this? Did you understand Kc and Kp? They can both be used to find out equilibrium constant. This is equilibrium constant in terms of concentration. This is equilibrium constant in terms of partial pressure.
You can expand that, right? Fraction. Each P is equilibrium.
You can also have Kx.
Then you get Pt common, right?
When you are doing this for mole fraction, same thing. Mole fraction of A, sorry, mole.
Pt, right? Pt will be common. T to plus P T minus T plus
So you can have K equilibrium constant in terms of mole fraction. Guys, time and again, what are we talking about? We are talking about the active mass. We are talking about the amount which is going into the reaction. Done? Okay. So let me give you the homework. Your homework is just exercise 1, in text exercise 1. Only exercise 1, but you have to do it today. Okay. Assignment in text exercise 1 today. So when you come back tomorrow, I want you to have done this first exercise. Done? Perfect. Thank you so much. Yeah. Okay guys, all of you, please open the live session and just like the session. Thank you.